What I thought I'd do is show you a tool we made to make some scrolls for a railing. We could buy this pattern here, but it wasn't quite what we wanted. We wanted smooth flat bar, not hammered bar, and that pattern isn't exactly what we wanted. And since we couldn't buy what we wanted, we decided we needed to make it. So what we did was, using our tubing roller, we made some dies and some tooling, and we made all the scrolls. There's about 50 of them right there. Each assembly has 2 pieces to it, so that'll do about 25 scrolls. And I think we decided we had about 50 to do all together, so that's about half of them there. Here's basically what the pattern looks like when you nest the 2 scrolls together. Those center kinks get cut out and a ring gets welded in and ground smooth, and then there's a medallion that goes in the middle and some smaller scrolls coming off the end. That'll be pretty easy to make, but the big ones were the real challenge. So what we decided to do is start with our tubing roller, and the way it works is all 3 of these rollers are driven. You step on the pedal here, push one pedal and it goes one way, push the other pedal and it goes back the other. And what you can do is advance the top and middle roll down by pushing the button. You can see the numbers changing. And what that does is takes the top middle roll down and puts pressure on your material, and once you get down to a certain amount of curvature as measured by your digital readout, then you can roll the material and that'll put the curve in it. Well, since this is a powerful machine with a lot of gear reduction, we decided just to use one shaft to spin our die with our material kept straight, supported out on one side, and basically just roll the material up around that die, and that would create our scrolls. And I'll show you actually how we did that. So here's our drive flange that goes on the bender. Basically we took a piece of DOM tubing and machined the ID to fit the outside diameter of the shaft. And then we milled a slot in it with our Bridgeport mill, since we didn't have a broach to put a slot in it. We machined that slot in there and then welded a piece of plate on it to tie it back together. We flame cut a ring and then machined all surfaces of it with a bolt pattern to bolt to this bigger plate. And there's a couple different steps here you can see, and the reason that is because the shaft is a smaller size. We still need to be able to get the washer in there and get the nut on it and get it tight. So we need to be able to put the nut on and then bolt our big plate with our die on it. So we kind of had to do it 2 different pieces. So as you can see, this fits onto our shaft. We put that on there like that. That slides on there. Then we put the nut on, tighten it up, and then we bolt the big plate to it. And basically the way our die works is here's our die. A scroll is basically a spiral with an increase in radius. So I drew that in AutoCAD, and then we had a local company, CNC Plasma, cut that for us so that the shape was correct. Computer controlled plasma cutter. So basically the design is you stick your piece of bar that you want to bend in a slot, and that holds it in place. And you can see our die is spaced off of our plate a little bit. And then so the piece of material goes in there, and then you apply pressure and you basically bend it on around the die. And then there's your scroll. We had to do it in two different steps because you can't have the die coming clear around here where it's in the way. So basically we bend the piece of material to this point, and then we bolt on that second die right there that you can see, and that brings it from that point on around once the material's bent. And so that's basically how it works. Our first whack at it, we were hoping to just support the material out here and let the twisting motion do the bending. But what we discovered was that just put a big belly in it, and it didn't bend it a very tight radius on the smaller radiuses, and there was a lot of spring back. So then what we did is came up with this mechanism here, and it's basically a hydraulic follower. The challenge is that the radius is continually increasing, and so where a lot of our other dies, for like our tubing bender over there, you have a fixed die, and then you have another die that drags around the outside of it and forms your material to your die. But that works because the radius is constant. But with a scroll, your radius is always increasing. So we built this contraption, a hydraulic follower, and I'll show you how that works here. One of the challenges of doing the hydraulic follower was we wanted to have the support structure for the hydraulic ram. The bender shaft goes right through here. We wanted it to attach to the bender shaft on each side of the die, so the die goes in the middle here. And that way the force from the follower is this way, and the two bearings on each side of it are pushing that way, and that way the shaft isn't bending, but it's supported on each side. If we had this framework attached to the frame of the bender and just pushed on it, that shaft hanging way out from over here would have a large cantilever load, and we ran the risk of bending the shaft. So on the outside it wasn't too hard to support. We machined a ring and we bought a bearing, pretty inexpensive bearing at Whistler Bearing, maybe $50 for that bearing. And it goes on this little stub shaft we machined. And the bearing fits right there, and that supports it not too bad. On the inside though, we had the problem of our hub is there already, and we looked into the bearings that would fit this, that were that big, and about $500 minimum. So what I figured was, I figured a couple thousand pounds of force on the die, and you divide that by 2. If there's 2,000 pounds of force here, and you divide that by 2, that's 1,000 pounds of force on each side. And so I figured the area in square inches of that of this ID, and looked up in some charts what acceptable loading was for a greased sliding surface. Since it's only 6 RPM, it's not really high-speed rotation. And we calculated that the load on that surface, with it being greased, would be in the acceptable range. So that's how we ended up doing it. We just machined this ring. I think there's 3 thousandths clearance between this ring and the outer diameter of the hub right here. I actually had to machine a second ring, slide it on and weld it, because we weren't originally planning for that, until we figured out we had to do the follower. And that's how we solved our problem. Now, to get it on the machine, we also had to locate this grease ring with some dowel pins. So you can see there's a joint here. This is welded to the grease ring. Let me get a better angle here. This is welded to the grease ring, and the grease ring arms are attached to the arms of the rest of the hydraulic follower with dowel pins and 2 half-inch bolts. So the dowel pin aligns it, and the 2 half-inch bolt clamps it together. That way our shaft alignment between the two surfaces is exact. The fit on the dowel pin is about half a thou on each one. So the dowel pin aligns it down here at the bottom. So here's the dowel pins on our arms for our grease ring. You can see one has one, and one has got the receiver hole, just a female hole, so that you can't ever mix it up and get it backwards, get the alignment wrong. Another thing to note is we kind of built some break points into it. You can see that our receiver arms are just barely welded to our grease ring. They're TIG welded, so they're good and strong, but we didn't fully weld them for a couple reasons. Number one, we didn't want to distort this hole. We had to machine that hole on the lathe, so this part can't spin with the arms welded to it. So we didn't want to, anytime you weld, it shrinks and changes the shape of things. So if we welded that fully, we felt that would egg shape our hole, and then we wouldn't have a good fit. And 2, we wanted something that if something went wrong, if we were applying too much pressure, we wanted something to break. And we wanted to break right here and here, or here and here. And we didn't want to bend the shaft or mess up any of the other expensive tooling that we've built. So we kind of made this the sacrificial lamb, so if something breaks, it's going to break right here. And same thing for the arms with the bearing in it. We just welded the tops and the bottoms and nowhere else. And we pressed the bearing in afterwards, after it cooled, so that the heat from that didn't affect the bearing, melt the seal or hurt the grease or distort it.